and then we'll be sharing the recording with everyone. So the recording has been started, so we can get started with today's workshop. So today's agenda is as follows. We will be covering all of these 8 points which are mentioned on the screen. First, I'll start with my story because that will also give you a reason for why we are conducting this workshop in the first place. What's the agenda for this workshop? And if I tell you my story, I think you will resonate with it much better. Second, we'll come to the problems with traditional machine learning as I discovered myself in my PhD journey. Then we will talk about scientific ML. Before going into the black hole modeling project, it's really very important for all of us to be on the same page with respect to scientific machine learning. So we will tell you about what is scientific ML, the introduction to scientific ML, what are the prerequisites, what do you need to learn, and then we will jump into the project. We have constructed this entire webinar so that it's beginner friendly. And if some details are unclear, the recording will be shared to all of you anyways. And then we will get into live coding when we come to the black hole modeling project. I'll show you the code. Towards the end, we will talk a bit about the scientific machine learning bootcamp, and then we will talk about research. So if you have attended our previous webinars before, you will know that we really place a lot of importance on research. Doing projects is not enough. We need to convert those projects into research publications. Finally, we will have a dedicated slot to the Q&A. So if your questions are not answered in the chat, it's fine. We will take them towards the end. But as I mentioned, please keep on asking questions in the chat, because what happens is that when we cover some topic, you get an immediate doubt, and that doubt you can forget towards the end of the webinar. So it's better to ask it in the chat when you have the doubt. So let's get started. First, I'll tell you a bit about my story and why we are conducting this webinar in the first place. So I graduated from IIT Madras in India with a BTech in mechanical engineering. This was in 2017, and at that time I had no clue about machine learning. In fact, then later I joined MIT for a PhD in mechanical engineering. I came to Boston, and at that time I had a dream of becoming a professor in the long run. So then this was my dream, and I started my PhD journey with this dream. What happened after 2 years was that I went to a career fair at MIT, and I looked at the companies and the startups which had come to the fair, and I saw that there were really very few jobs in core mechanical engineering or pure mechanical engineering. All the jobs, all the startups which had come, I would say 80 to 85% required the candidates to have some knowledge of machine learning or artificial intelligence. Even the jobs which were there for mechanical, they required a mechanical plus machine learning expertise. And this made me really very demotivated. And I felt like an imposter syndrome that everyone around me was talking about machine learning, artificial intelligence, and I had no clue about these topics at all. So slowly what happened is that I started losing interest in mechanical engineering completely. This was at the end of my second year. It was one of the lowest points of my PhD. And honestly, I thought of quitting MIT at that time. But what happened is that there were a number of things which happened which led me to switch to machine learning. So I switched completely from mechanical to machine learning. And what happened in the next 3 years completely changed my life. I found a new research group in ML that turned out to be luckily in scientific ML. And at the end of the next 3 years, I published machine learning papers with today I have 400 plus citations. And I defended my PhD thesis at MIT in machine learning itself. After graduating, companies reached out to me like Meta, Amazon, Julia Computing, etc., to offer jobs in machine learning. So this webinar is all about how I made this switch to machine learning and how you can do it too. The story or the pathway which we are going to describe today is very generic to all the people who want to switch to ML. Mechanical engineering is just my reference point, but you can apply it to your story also. One thing which I want to do at the start of this webinar, which we have not done previously, but it's the feedback which we have received. I am going to send this form right now on the chat. This will really help us to get an understanding of your main field. So can you please fill this form as quickly as you can? When I reach slide number, I think 12 or slide number 13, I'll look at the responses which all of you have filled. It's very simple, just 5 questions. I basically just want to know your field of study and your ML knowledge. That's it. Okay, so let me continue for now. When I come to a later slide, I will look at the form responses which you have filled so that I can tailor the rest of the webinar accordingly. At the end of my PhD, here are some of the research papers in machine learning which I published. By the way, all of these papers are in the field of scientific machine learning. None of them are in traditional ML. We collaborated with the US government of various countries to apply scientific machine learning to model the COVID-19 infections. So my PhD turned out to be very impactful towards the end. And as I said, at the end, I received interviews, job offers with all of these companies. The reason I'm sharing all of this with you is because uh, you will get some motivation that what might be possible for you at the end of this webinar. The tools and the story or the pathway which you will learn today can land you in such a place where I eventually landed. So the main question which we will try to answer in this workshop, in the initial part at least, is how was this possible for me? How did I switch to ML from mechanical engineering background? I had no clue about computer science. I had not taken a data structures course at all. So the first myth which I want to break for everyone is that when I wanted to switch to machine learning, I had this conception in my mind that machine learning is only meant for computer science students. And I felt a bit insecure about it. I had not taken any CS course. I had no background in formal CS. So somehow in my mind, this thought had formed that if I don't know about CS, I won't be able to switch to ML. And I want to tell all of you that this is completely wrong. I strongly believe that whatever background you are in, whichever stage of your life you are in, you might be a student right now, a working professional, you might be in between careers. All of us can transition to machine learning. It's completely possible. How do I know this? Because I was in a similar position, right? I was a core mechanical engineer. So if I can do it, I believe that everyone on this call, it's possible to do. It just you need the right pathway. So I discovered this pathway accidentally. I discovered scientific machine learning accidentally, but now I'm conveying all these learnings to you. So my main realization when I look back now, the reason I could transition to machine learning was three things. First is that now I realize that the way traditional machine learning is taught is not correct for engineers. I accidentally discovered the new field of scientific ML, which changed my life. Secondly, when I was in the transition period, right, when I wanted to quit MIT, I met a senior at my college and he really told me that you can transition to ML. And that gave me the belief. So sometimes we need someone to tell us that you can do this. So this webinar can serve as that point of motivation to all of you that if for some reason you think that you cannot transition to ML, I want to give you that confidence right now that you can also do it. So when my senior told this thing to me, I really it became very important for me, and I suddenly started believing more because he told me that I could do it. So the second thing is I had this belief that you can make this transition. And third thing, which is very important, many students make this mistake is that what students do is that they have quick ML projects. Maybe they run a project on Kaggle, maybe they run a project on GitHub, and they add it to the resume directly. This is not the correct approach because everyone can do it very easily. What I did instead is that I focused on research. I did not update my resume by adding quick projects. I converted those projects into research publications really. And that made a lot of difference for me. So let's get started with the first point, which is what's the real problem with traditional ML for engineers? And I want to explain this with a practical example. If you go to this link right now, which I'm sharing on the chat, please go to this link. This is the MIT's course for machine learning. All of these lectures are completely available for free, by the way. If you go to this link and click on the course syllabus, you will see the syllabus which they have. And this is pretty much the syllabus with all introductory machine learning courses. First, these courses teach you linear classification, then they teach you non-linear classification, then they teach you neural networks, then they teach you unsupervised learning, and then they teach you reinforcement learning. That's fine. But now I want you to look at the projects which you do as part of this course. Look at project one, automatic review analyzer. Project two is digit recognition. In fact, in this webinar, I have made a list of all the beginner level projects which you usually do. And automatic review analyzer is one of them. Digit recognition is one of them. Collaborative filtering is one of them. Text-based game is one of them. Do you see the problem with these projects? The first major problem is that they don't show you how to combine machine learning with your domain. Let's say I am a mechanical engineer, or I am an electrical engineer, or I am a biology person, or I am a chemistry engineer, right? What I should be really shown is how do I combine machine learning with my field? As a mechanical engineer, how is doing a project on automatic review analyzer useful for me at all? It does not teach me anything about my domain, right? I have spent so much time in mechanical engineering. I would like to do a project which combines mechanical engineering with machine learning, not this toy project. So now let me go to the form which all of you have filled. There are 81 responses. So let's see the summary. Okay, so look at the distribution of the fields in this form. There are people from mechanical engineering, civil engineering, electrical engineering, biological, chemical, physics, finance, fluid mechanics, and many other fields like chemistry, biomedical, etc. Right? Now you have spent so much of your time in all of these fields. How is doing a project on, let's say, automatic review analyzer or centim digit recognition related to your main field at all? It's not, right. That's why the traditional courses are not correct for all of these fields. Ideally what you should be doing is that let's say, let's look at electrical, right? 11 people in this call right now have studied electrical engineering. Instead of doing a toy project on housing price prediction, what if you do a project which combines electrical engineering with machine learning, right? Wouldn't that be amazing? In fact, that such a project will be much more impactful. That's the main point which I'm trying to convey in this first realization, that these projects don't show you how to combine machine learning with domain specific knowledge. They don't. These are toy projects, and they are toy projects, so we cannot even publish research with them. If you do a project on, let's say, Netflix movie recommendation, you cannot publish research with them because it's a toy project. You have not done anything new here. Everyone would have done these projects and have it on their resume. What ideally you should be doing is, without leaving your main field, which has been seen in all these forms, let's say robotics, right? Without leaving robotics, you should do a project which combines ML with robotics. That's where scientific machine learning comes into the picture, right? Now imagine you do these projects instead. Imagine that you use machine learning to model COVID-19 infections in all the regions of the world. This was my project, by the way. Secondly, as a chemical engineer, so let's say, how many of you in this call, chemistry, there is one person, biological sciences, two-person, right? What if you do a project at the intersection of, let's say, chemical engineering and machine learning? So the project is, how do you recover a chemical reaction uh, from the data alone? Let's say you do this project, you are given the data and you recover the chemical reaction using machine learning. Secondly, let's see physics. This is, by the way, the project which we are going to cover in today's lecture, black hole dynamics. Let me see how many of you are physics. Okay, it's a lot, right? There are 17 people in this call who have studied physics. And scientific ML is a beautiful field to combine physics with machine learning. In fact, this is what we are going to do today: how to use machine learning to predict black hole dynamics. As a physicist, wouldn't this project be much more relevant to you than those toy projects which we have seen earlier? Similarly, I assume there are many data scientists and economics people also in this call. There are many here. So why don't you use ML to predict economic market forces like demand and supply? Then ML for biochemistry, machine learning to analyze fluid mechanics and climate problems. This is where scientific ML comes into the picture. It's that field which combines your domain with machine learning. That's why it's called scientific machine learning, science plus ML, right? So scientific ML is a field which is meant for all of you who are in this call, really. It's really the discussion which we are going to have right now is very relevant for you, because the projects which are taught in traditional ML courses are toy projects. The advantage with these projects is that, let's say if you do a project on black hole dynamics, right? The advantage is that you will first of all have a strong foundation in ML, and not just that, you will learn how ML can be integrated in your field. So you don't have to leave your main field of physics, let's say. Second, you can do independent research with these projects. Let's say I teach you this black hole project right now, and you go home and you build something on top of it, or you make some modifications to it. I'm pretty sure there are very few people in this world who would have done that thing. So you can convert that project into research publication as well. That's what I did, by the way, for my PhD. I started with a project in scientific ML and converted that into a very strong publication. Third thing which happened for me, so I can say this confidently, is that these projects you can add to your CV compared to the previous projects because these are unique projects. Not many people will have these. So this will open doors for you in software companies, startups, etc. What's happening right now is that, let's say, let me address robotics people in the room right now. So let's say you are one of the 6 robotics people in the room, right? The companies which come for robotics, they are looking for people who not just have robotics knowledge but machine learning knowledge also. So if you have done a scientific machine learning project at the intersection of ML and robotics, you suddenly become a strong candidate, right? Similarly, for mechanical, electrical, all the fields, if you are a candidate who has domain knowledge plus ML knowledge, it positions you in a very strong manner. Uh, okay, so many other things actually these projects had a benefit to you is that, so there are many professors right now in top universities who are looking for students who know about scientific ML, and not many people know about this field. So if you do a project in scientific ML, you can reach out to professors in top universities like MIT, Stanford, Berkeley, etc., and start projects with them. I know this for a fact because my advisor is the leading researcher in scientific ML at MIT, and he told me a lot of times that there are very few people in scientific ML right now, and he is looking for collaborators, right? So, see, traditional ML fields are pretty saturated. NLP, computer vision, data science, it's pretty saturated. Scientific ML is a new field. It just picked up in the last 4 or 5 years. Right now, we are in the perfect position to do these projects. 5 years earlier, there was not too much knowledge about this field. 10 years later, this field will also be saturated. Right now is the sweet spot to be learning about this field. If any of you in the call are looking to apply to grad school, right, these projects will also improve your grad school profile because, as we all know, for computer science, the application process is really competitive. Everyone wants to apply to CS these days. So if you want to distinguish yourself, or even for any field, let's say elect, mechanical, physics, if you want to distinguish yourself, if you have a scientific ML publication, right, it will do wonders for your profile. Okay, enough of the motivation now. I hope you have all understood the need for scientific ML in the first place. Now let's come to the fun part, which is intro to scientific ML. Many questions are being asked in the chat about how do you proceed with the scientific ML problem with ODEs, PDEs, etc. Right? So let me try to now cover this in a lot of detail. So please be attentive in this part. Okay, so let's get started. Essentially, at its very simple thing, scientific ML is the branch of machine learning which combines ML techniques with domain knowledge, as I already mentioned. So, as a physicist, there are 20 physicists in this room, I think. So, scientific ML will be combining physics knowledge with machine learning. So why this field has picked up in the recent years is that if you look at traditional ML, it's like a black box, right? It's not interpretable. It gives good results, but if you ask questions that why is this working, no one knows. It just works. Scientific ML is like shining a torch on this black box. Since you include physical equations, since you include ordinary differential equations, since you include partial differential equation, there is science which is added to machine learning. So suddenly the black box has become interpretable. You can ask questions to why are we getting this result? And you actually get answers. That's the beauty of this field. As engineers, we want answers, right? We cannot just look at black boxes. We need to know how things work. That's why engineers really like this field of scientific ML, in my opinion, because it's like shining a torch on the black box of ML. So, using scientific ML, we combine the power of neural networks with the interpretability of scientific structures. This is a very important sentence. So, scientific ML, right? So, ML part is neural networks, and the science part is scientific structures. And you might be thinking, what are scientific structures? And I'm coming to that in a minute. But the ML part is neural networks. So, think of it this way: neural networks are powerful, but they are not interpretable. Scientific structures are interpretable. So you combine the power of neural networks with the interpretability of these scientific structures. Now, as I already mentioned, whichever field you are in, as you are filled in the form here, what I'm going to teach you right now is relevant to all of these fields. All of this. I have seen research papers published in scientific ML for every single field of this. So don't think that this is not relevant for me. I can give you papers for all of these fields. And in fact, I'll show you some research papers at the end of this webinar. Okay, so Dr. Christopher Rakaukas was my PhD advisor at MIT. Let me show you his profile. I'll also share it on the chat. So this person was my PhD advisor at MIT. He is now the lead researcher of scientific ML in the whole world. You can look at his profile. So he defines scientific ML like this. According to him, it is model-based data efficient ML. So traditional ML requires a lot of data, right? But in scientific ML, since you are using the physical structures, the amount of data which you need is less, which is good. Because in a lot of real life scenarios, data is not available. Data is the resource now, as like land, time, and money. It's a scarce resource. So scientific ML reduces the need for too much data. That's another advantage of this field. Okay, so if you have forgotten everything up till this point, it's fine. Just remember this, that scientific ML uses data and domain knowledge, right? Now you might be thinking, what do you mean by scientific structures? I've used this word scientific structures a couple of times, right? I have a very specific definition when I think of scientific structures, and some students have also asked this in the chat. When I say scientific structures, I mean ordinary differential equations or partial differential equations, really. And I'm assuming people in this call know about ODEs or PDEs. Can you just type in the chat yes or no if you have studied ODEs or PDEs before, or if this is completely new to you? Okay, it's quite good to see that almost everyone has knows about these topics. Great. So that makes my job a bit easy in this section. But still, some people are saying no. So I will still give an overview. Don't worry. So basically, an ordinary differential equation can be thought of as a rate of change. So if you have invested in a stock, let's say if you invest in Nvidia stock or Facebook stock or Apple stock today, and if you want to find the rate of change of that stock, if you write an equation like this for the stock, that's an ordinary differential equation where it's how the stock varies with respect to time. The best and the simplest way to think of an ODE or an ordinary differential equation is the Newton's second law of motion, right? So we all know force equal to mass times acceleration. This can also be written as force equal to mass into d square x by dt square. Again, here the rate of change comes. So this is an ordinary differential equation. This shows up in a lot of places like biology, ecology. There is this logistic equation. This is also an ordinary differential equation because it shows the growth of population with time. You might be surprised, but many things which you see around you, right? There is usually an ODE at the heart of it. Let me give you an example. When the COVID-19 pandemic was happening, right? Uh, so let me search COVID-19 pandemic and let's see this graph. So as a person, let's say for COVID-19 pandemic infection count. So if you see the infection count, we all know how it increased exponentially. There are multiple waves. But do you know that there is an ordinary differential equation at the heart of this? If you know about this equation, can you just type it in the chat? What if anyone knows what's the equation? What's the ordinary differential equation for epidemiology? Which was invented about 120 years back. Sayantan has already mentioned it correctly. It's the SIR model. So the SIR model of epidemiology was invented in 1917, I think, and basically it divides the population into three compartments, and that can be written as a set of ordinary differential equations. Let me see if I can get these ODs. Yeah, right here. So this is the rate of change of the susceptible population, rate of change of infected, and rate of change of recovered. This is an ordinary differential equation. Similarly, any field which you are looking for might have an ODE at the heart of it. Someone has asked control systems, right? It might have an ordinary differential equation at the heart of it. This can be the start of a scientific ML problem. So these are scientific structures, but there is one more scientific structure, and that's a partial differential equation, right? And the difference between ODEs and PDEs is very simple. In ordinary differential equation, there is just one independent variable, right? Usually it's time or it's space. In the case of partial differential equation, there are two or more independent variables. So let's see an example. Here is the heat equation. Does anyone know what this operator is? This symbol here, grad square U. What's the name for this operator? Does anyone know about that? Correct, del square, but the del square is called a Laplacian operator. So Laplacian or Hessian, many people know about this, but for those who don't know, This operator, when you expand it, it is d square u by dx square plus d square u by dy square plus d square u by dz square. So if the temperature is the variable u, this equation represents the variation of temperature with time as well as space. So there are more than one variable. Uh, that's why it's a partial differential equation. Many people in this call are, I think, computational fluid dynamics. So there are three fluid mechanics people. And I'm pretty sure many of you might be knowing about the Navier-Stokes equation. It's one of the most famous partial differential equations because you are sitting in a room right now and air is flowing, right? The flow of air can be modeled with a Navier-Stokes equation, where u is the fluid velocity, and here you have the fluid velocity variation with time as well as the space. That's why it's a partial differential equation. These are scientific structures. ODEs or PDEs usually. So in your field, there are many people who have asked how is scientific ML applicable to cosmology, astronomy. You'll see this in detail subsequently. But right now, if you can think of an ordinary differential equation or a partial differential equation in your field, you have the start of a scientific ML problem. And in all the fields which have been mentioned here, there is usually an ODE or a PDE at the heart of all of these fields. Okay, so now let's go to the second ingredient of scientific ML. The first ingredient is scientific structures, right? As let me go here, scientific structures. The second ingredient is neural networks. More specifically, there is a property of neural networks which is called as universal approximation theorem. Let me actually see another question which all of you have answered, which is ML knowledge. So I can see that 30 people in this call are complete machine learning beginners. 35 people have a basic knowledge and 24 people have an intermediate knowledge of ML. That's fine. So one property which I want to show you all is that a neural network looks something like this, right? There are input layers, there are hidden layers, and there is an output layer. There is one property of neural networks which is really important for scientific ML. And that property is that if you increase the number of neurons, a neural network can essentially approximate any function out there. So you take any complicated function, a neural network can approximate it if you increase the number of neurons. Let me give you an example. Let's say our underlying function looks like this. It's complex, right? If it turns out that if you have 50 units in the neural network, if you have 100 units, so these are called units, you can approximate this function exactly. So here is the trained neural network which approximates this function. Amazing, right? But it can even approximate more challenging functions. Look at this function, for example. Look at this completely concave function with a lot of peaks, lot of valleys. But it turns out that a neural network can exactly approximate this function as well. All you need to do is just increase the number of units. All you need to do is just increase the number of layers. That's it. This is the property of neural networks, which all of you need to remember. Now, if you are thinking that I am a complete ML beginner, I don't know what neural network are, there is this list of transition to ML resources document, which I'm right now sharing in the chat. Don't know why this is not loading, but when this loads, I'll share this document link in the chat. In this document, basically, I've mentioned, yeah, got it. So, share the link in the chat. Please check this out. In this document, I have mentioned a lot of resources for transitioning to machine learning. So if you are a beginner, if you come in this category, if you are one of these 30 people in this call, go through this list of resources. In fact, how many of you have been through our machine learning teach by doing series or the neural network from scratch series on YouTube? So I myself have recorded around 36 videos of machine learning and around 35 videos in neural networks. All of them are available for free on YouTube. So Rajata shared these links. If you want to learn about ML and deep learning, just go through these playlists. They are quite comprehensive. So I've covered everything from scratch. So look at neural networks from scratch. It has around 30 lectures and it covers every single thing. So you can bookmark this. I've added the links here, so no need to worry. If you have got access to this document, you can start learning the ML concept. For now, the only thing which you need to remember in this call is that neural network are universal function approximators. No need to read this on the slide right now. All this text basically says that a large enough neural network can basically approximate any function out there. That's the second thing which you need to remember. So remember the two ingredients of scientific ML. The first ingredient is understanding ODEs and PDEs, and the second ingredient is understanding the universal approximation theorem, which means that neural networks can approximate any function. So keeping the universal approximation theorem in mind, what we do is we mix neural networks with differential equations. That's all what is done in scientific ML. So there are usually three pillars of scientific ML. How many of you have heard of physics informed neural networks? You can just type it in the chat if you have heard about this term. If not, it's fine. There are some people who have heard about this term. There are some people who might not. It's fine. So there are three pillars of scientific ML: physics informed neural networks, neural ordinary differential equations, and universal differential equations. Today we are not going to cover all the pillars. For our project right now, we just need this third pillar, which is universal differential equation. In universal differential equation, what we basically do is we replace missing physics in an ordinary differential equation or a partial differential equation with a neural network. Let me repeat it again. Let's say if you have an ODE or PDE, but if you have some parts of that ODE which are not known or some physics which is missing, you replace the missing physics with a neural network. And why can you do that? Because neural networks can approximate any function out there. So we start with an ODE or PDE, then we look at the terms to replace. If it's a missing ODE, if the ODE does not capture some complex phenomena, we replace that with neural networks. And that is our scientific ML equation, underlying equation. And that's also called universal differential equation. And you will see this in practice right now. When we implement the black hole dynamics project, this is what we are going to do. We are going to look at an ordinary differential equation, and then we are going to replace terms of that ordinary differential equation with a neural network. So just to give you an example, this is an epidemiological ODE. If you do not know some terms, you are going to replace those terms with a neural network. That is the main essence of universal differential equation. And this is the essence which we are going to follow when we do the black hole dynamics project. So now all of us are equipped to understand how to go forward with the black hole dynamics problem up till now. If you have forgotten everything in the past, just remember that we are going to mix neural networks with ordinary differential equations. And why can we do that? Because neural networks are universal function approximators. Up till now, you should have also received links to these resources documents. So now we are ready to begin this project. First, I want to motivate this project a bit. So I want to play a video. And can you tell me if you can hear the sound? I'm not sure. First of all, this video should play. It is a bit. Mm, it is a bit size. The size of this video is a bit large, but this video essentially explains gravitational waves. Can you hear the sound?
What are gravitational waves? It all
Yes,
starts
we
back
can
in
hear.
1915 with
So let
Einstein.
me play this again.
What are gravitational waves? It all starts back in 1915 with Einstein. He hypothesized that all objects with mass would warp the fabric of space-time. If their mass is great enough, those distortions could cause other objects to fall into them. This is what we call gravity. Einstein also predicted that these distortions could travel across the universe, stretching and squeezing space and time as they move. And this is what we call gravitational waves. Later, researchers realized that if two particularly giant masses, like two black holes, are trapped in each other's gravitational...
This is very important for our project. When two masses are trapped in each other's gravitational field, they emit gravitational waves.
fields, they should start to spiral in towards each other. And so would the distortions they make to space-time.
So when particles are orbiting each other, or when two black holes are orbiting each other, or one particle is orbiting a black hole, they usually emit gravitational waves. And as these particles come closer to each other, the gravitational wave amplitude actually starts increasing and its frequency starts increasing. For now, you need to know that when there is an object which is orbiting a black hole, or if one black hole is orbiting another black hole, like what you saw over here, like here, then gravitational waves are emitted. Now, the major discovery which happened, and all of you might be knowing about this, is that LIGO detected gravitational waves. And this was one of the major breakthroughs of the last 2 decades. I feel that this was Einstein also thought this to be impossible, but we actually detected gravitational waves. Uh, in the video, if you watch it further, they also show the facility which detected these gravitational waves. So there is a bit of physics involved to it. So someone is asked, what do you mean by emitting gravitational waves? It's a bit more complex, and I don't want to go into the physics right now because we are going to solve this problem in a bit more machine learning sense. I'll share the link to this paper and I'll share this video also with all of you. Right now, all you need to worry is that when a body is, let's say, orbiting a black hole, gravitational waves are emitted, right? And we are able to detect these gravitational waves. And the detected gravitational wave is usually in the form of a waveform. So one more thing before that is that detection of these waves is also a good way to test the theory of general relativity. I'll come to that in a minute. But in our black hole dynamics problem, what we are going to do is that we are going to start with this detected gravitational waveform. So let me show you how it looks like. This is how a gravitational waveform looks like. So when a particle is orbiting a black hole like this, the gravitational waveform looks like this. To provide a bit of an intuition, look at this point when there, you can see here, the amplitude increases and the frequency also increases. This is the point when the bodies, when they are orbiting, they spiral towards each other. If you remember the video, when they spiral towards each other, the frequency of the gravitational waves increases and the amplitude also increases, as it's shown in this graph. And then they again spiral outwards, and this cycle actually continues. That's why this waveform has a periodic nature. This waveform is detected by us through the LIGO facility. And this is the starting point of our scientific machine learning project. So let me now move to the next slide. Okay. So this is the first thing I need you to keep in mind. This is the underlying data. Imagine that you are a person working at LIGO, right? And you have detected this waveform when an object is orbiting a black hole, let's say. That's the first thing. Second, as I told you, whenever a scientific ML problem is being constructed, there is usually an ordinary differential equation at the heart of it. And so here a particle is orbiting another black hole, right? So this is the ordinary differential equation which describes the motion of the particle. So there are two variables. You can see this first Greek symbol and the second Greek symbol. This is the radial distance of the particle and this is the angular position of the particle. And these symbols just show rate of change. That's it. So basically, when we solve this ordinary differential equation, we get the position of the particle where it is in that orbit. The key thing to note is that this is Newtonian dynamics. This does not include or factor in Einstein's theory of relativity. It turns out that if you plan to include Einstein's relativistic dynamics, then the equations actually become a bit more complicated. So look at these equations. It just contains numerator by denominator, right? And numerator by denominator. If you were to include some relativistic dynamics, here is how the equations change. If you were to include relativistic dynamics, there are some complicated terms which are added. No need to don't need to worry about what these terms are. All I want you to understand here is that when you look at this relativistic, or when you include the theory of relativity, there are some additional parameters which are added to the ordinary differential equation, which make the system a bit more complex. So just keep in mind that the motion of the particle here can be described by two ODEs. The first ODE is the Newtonian dynamics, and this is not correct because this does not include the relativistic effects. The second ODE is the relativistic dynamics. Now, here is the problem which you are going to solve as a researcher. Imagine that you are a researcher in the LIGO team, okay? And suddenly on one day you are so excited, you collect this data and you have this waveform data. That's amazing. And this is how the data looks like. As we see the oscillatory behavior, the increase in frequency and the increase in amplitude. Great. Now, the catch is that you don't know the underlying equations, or more in detail, more specifically, you only know about the Newtonian orbit. So let's say the relativistic corrections are not known. As the researcher in the LIGO team, let's say you only know about the Newtonian model. And if you have this underlying data, you know that this model is not going to match the data. So you don't know the relativistic or Einstein equations. Your challenge is, can you discover these equations from the data alone? That is your challenge. Let me repeat it. You have this data, right? And if you have an incomplete equation, you know this is not correct. It does not capture the relativistic physics. And you don't know the relativistic physics. Then what do? You turn to scientific machine learning. This is a problem which is perfectly suited for scientific machine learning. Why? Because what you can simply do is that the terms which you don't know, what if you replace them with a neural network? Let me repeat that. Remember, you know the Newtonian ODE, right? You know this idea is very important to capture. So please be attentive in this idea. You know this ordinary differential equation, which is the Newtonian physics, but you know that these equations are incomplete. You just don't know how they are incomplete. You don't know the terms of you don't know these terms. You don't know this cos, this sine, all of these things you don't know. So what do? You say that, okay, neural networks are universal function approximators, right? So can I replace the missing physics with neural networks? And this is exactly what you do in a scientific. Oh, I think my net. Am I audible? Hello. You are muted currently. Am I audible now?
Yes, now it's better. Can you explain this slide again?
Yeah, yeah.
We could not hear you.
Sure. So basically, the problem is that we have this Newtonian orbit model with us, right? Uh, I'll maybe disable the video so that it's more better. So we have this Newtonian ordinary differential equation with us, but we know that this is incomplete. In particular, we know that there are some additional terms which need to be added here, but we don't know what form these terms will take. So we don't know this relativistic physics. So we don't know these cos terms, all of these square root terms. So what do? We think that, okay, neural networks are function approximators, right? So what if I replace the missing terms with neural networks? What if I replace the missing physics with neural networks? And why can I do this? Because as I mentioned to you, neural networks can approximate any function out there. So technically, if this neural network is trained, it can recover this missing physics for me. It can recover the relativistic dynamics for me. And that is exactly what I'm going to do. You have the underlying waveform data. You have the underlying waveform data, and you construct the universal differential equation like this. You take the ODE which you have, and then you multiply the terms of this ODE with a neural network. And then what you will do is that you will train the neural network based on the underlying data which you have. You will train the neural network based on the waveform data, and then you will optimize the neural network completely. And the hope is that after you optimize the neural network, it will discover the relativistic physics for you. Isn't that amazing? Just based on data and some incomplete physics, you are now recovering the relativistic corrections using scientific ML. Do you understand now why it is called scientific ML? We take incomplete ordinary differential equations, or we take incomplete underlying data, and we replace or augment those with a neural network. And with this neural network, we can now capture missing physics which was not known to us. So even if relativistic physics was not known, using the power of scientific machine learning, we can capture those terms. I'll be taking you to code very soon, so you can relate this or visualize this in a much better manner. But for now, just remember this image. Remember where we are multiplying this neural network by. So this is the procedure. We will construct this universal differential equation. We will train the neural network based on the data, and we will try to recover the relativistic interaction. This is a perfectly framed scientific machine learning problem. And now you can relate it to your own field. If you have an ordinary differential equation, or if you have any equation, basically OD or PD, and if you think it's incomplete, you can replace terms with neural networks and try to discover the missing physics. That's the main essence of universal differential equation. Now we will be moving to the coding part, and in the code, I'll show you exactly what we will be doing. So up till now, hopefully you have got a visual or an intuitive sense of how to formulate a scientific machine learning story in the first place. And now we are going to go to code. The first thing which I want to explain when we move to the coding part. So let me move to the coding part. The first thing which I want to explain is the language which we are going to use. How many of you in the call are familiar with the Julia programming language? Can you just mention yes or no in the chat? I can see that mostly, I would say it's a 20% yes and 80% or 90% no. And this is completely fine. Mostly people are familiar with Python. But one thing which I would like to tell you right now is that Python is good for traditional ML tasks like computer vision, NLP. It's the best language, right? But Julia programming language is the best programming language for scientific machine learning. You can check it out. You can also search about Julia. It's one of the most innovative new languages. In fact, let me share with you one thing. When I told you at the start that I switched my research groups, this is the new research group which I joined at MIT. This group is called the Julia Lab, and it's that research group where the Julia language was actually invented. So Julia is much better than R. It's much better than MATLAB for scientific machine learning. For traditional machine learning, you can stick with Python. It's the best. But for scientific ML, especially Julia is an amazing language. And why do I say that? Because with a very few lines of code, you can solve very complicated projects. So for today's code, I'll show you how efficient it is in Julia. And if you know about Python, if you know about MATLAB, learning Julia will be very, very easy. Julia is actually simpler to learn than Python, in my opinion. This is the first thing to know when you think about the coding part. Now, this is how a coding snippet in Julia looks like, and we are going to come to this just right now. It's fully free. So Sailesh has asked if is Julia free, fully free, and Rohan has asked how is MATLAB for scientific ML. MATLAB is not actually. I would not recommend MATLAB too much for scientific ML. First choice is Julia, second is Python, then would come MATLAB. But please, Julia is the best for scientific ML. So here is how a sample snippet looks like in the Julia language. We'll come to the VS Code in a bit, but just want to show you how the snippet looks like. Julia programming language I already told you. Now, to solve any scientific machine learning problem, there are usually 7 steps which are involved, right? The first step is to load the relevant Julia packages. So Julia works in the package environment, which is a bit different than Python. Uh, the second is to generate the underlying data. So as I told you, we need this waveform data, right? To train the neural network, we need this underlying data. So the second step when we are going to look at the code is to generate the underlying data. The third step is to define the neural network, which will be used to replace the interaction term. So remember here, we are going to multiply the terms with a neural network, right? So we need to define how the architecture of the neural network is. How many layers does it have? How many neurons does it have? What is the activation function? We need to define all of these things. Fourth, we are going to define the universal differential equation. By that, what I mean is we are going to take the ordinary differential equation and we are going to multiply the terms which I showed you with neural networks. The fifth step is optimization. So as you might have already seen, the neural network is not optimized at the start. We need to perform gradient descent optimization to make sure that the neural network is optimized. We'll train the neural network and we'll visualize the results. Now, based on all of the people in this call, from what I've seen, many people are beginners. There are 35 beginners in this call, uh, 30 beginners, 35 basic, and 24 intermediate. So when I go through the coding part, there is a possibility you might not know, let's say, what an activation function is, or you might not, let's say, understand what gradient descent is or what the Adam optimizer is. It's fine. I'll share this recording with you, and I've already shared all of these resources with you, right? So, for example, in the ML Teach by Doing, I explain everything from scratch. So you'll find relevant lectures here. For now, just try to understand as much as you can when I go through the coding section. I'm going to do my best to make sure that you understand the basics so that you don't feel it's difficult. Many questions in the chat are asking about the Julia language, its syntax. You will see in a bit when we come to the VS Code. Now let's dive in the VS Code. But remember these 7 steps: loading packages, generating the data, defining the neural network, defining the universal differential equation, optimization, training the neural network, and visualizing the results. Let's get started. Don't worry, recording will be available. So even if some parts you don't understand, you can go through it again. That's how we construct all of our webinars. Now I'm going to go through the VS Code interface. So let me stop sharing here and share my VS Code screen a bit. Can you see the screen?
Yes, we can see it.
Okay. Should I zoom in a bit more or it's fine?
You can zoom in a little bit. Yes, yes.
Sure. Let me zoom in a bit so that it becomes a bit more clearer to everyone. Okay. So this is the code. This is the black hole dynamics code. We'll be sharing the code with you. No need to worry. Okay, so the first step, as I told you, is loading Julia packages. So in Python, you also have to import packages and install packages. In Julia, it's the same thing, but the packages are named a bit differently, right? So here are some of the packages. So we are going to run differential equations. So we need this ordinary diffq package. Then we are going to define neural networks. For that, there is a package called Lux. We are going to do plotting. So there is a package called plots, and we are going to do optimization. So there are these three packages. This part of the code is usually pretty standard. So you don't need to memorize these packages. When I share the code, when you apply scientific ML for your problem, you can just copy this thing, because these packages don't usually change. So just remember that there is a package for deep learning. It's called Lux. There are three packages for optimization. Then there is one package for defining the differential equation. That's it. So this is the first step, loading the Julia packages. And I've already loaded these packages, so I won't take some time over here. Now, if you look at the script, you will see that it's a bit similar to Python. There are some variations here and there. So we have defined the packages, right? That's step number one, which is done. Now we have to generate the underlying data. And we are going to generate the underlying data from the equations. So let me first define the Newtonian model. So I showed you the Newtonian model, right, in the slides. You remember these two Greek symbols? Here is how I can define it in Julia. It's exactly like writing on a whiteboard. So this is the function for the Newtonian model. This is an ordinary differential equation, and that's why I love Julia really. It's just a very clean interface, and it's like you're writing on a whiteboard, so it's very intuitive. So this is the Newtonian orbit model, and this is the relativistic orbit model. Remember, we do not know this, but I'm just showing it to you here that it's a bit more complex. So the Newtonian orbit model is simpler, and the relativistic orbit model, as I already showed you in the slides, it has some complicated terms. Great. Now what we are going to do is that we are going to generate underlying data first of all. So to generate the underlying data, we are going to run the relativistic ODE. You can get it from real life also, but right now we don't have the LIGO measurements. So I'm just going to run the relativistic ODE to get the underlying data. Imagine this is the true data which you have with you. So I'm running this ordinary differential equation right now to get the underlying data, and you will soon see a plot appearing on the screen. So look at the right hand side of the screen. As the LIGO researcher, this is the underlying data which you have with you. This is the true waveform data which you have observed. And in Julia, the way you run ordinary differential equations is through this ODE problem. So you have to define this ODE problem, and that's how you run the ordinary differential equation in Julia. So I'm just going to minimize this plot a bit so that you can see the code a bit more cleanly. So remember, we have generated underlying data. That was the step number two. In when you actually run scientific ML problems, you may get this data from GitHub. You may get it from some sources which is already there. If data is not available, you can use simulated data. You can also add noise so that it mimics real life closely. The third step is to define a neural network. The neural network which I am going to use here is we are going to look at the following neural network, which has two hidden layers, and it has 32 units in the first layer. It has 32 units in the second layer, and it has the cosine activation function over here. Now, this is the part which is called hyperparameter optimization. You might be thinking, how did I choose this neural network with these many parameters, right? There you can choose it to have any number of units, any number of layers. Usually, this is an iterative procedure. You need to fix on one architecture, and you need to see the loss function, and then you need to keep on varying the architecture. Awesome. So we have defined the neural network here. Now, let me run the neural network output. Actually, before that, we have to define the universal differential equation. So let me go to step number 4. Step number 4 is defining the universal differential equation. And as Jeet has correctly asked in the chat, why not ReLU or sigmoid? Good question. The only reason I used cosine is because it's an oscillatory thing, right? So it turns out cosine does a good job. When I share the code with you, Jeet and Abhay, both of you can try ReLU or sigmoid actually. You'll see that it does not work as well. You can try cosine, sine, you can try leaky ReLU, sigmoid, many of these things you can try. Eventually, you will see that ReLU or sigmoid stagnate a bit. And it also makes sense from the data. It's oscillatory, so cosine and sine actually work the best. Okay, now we have to define the universal differential equation. So it's very simple. What we just do is that you remember the Newtonian physics. It had this term, right? This term. All we are going to do is we are going to multiply this with a neural network. So that is exactly what I'm doing over here. See, we are multiplying the first term with a neural network and we are multiplying the second term with another neural network. This is the main part of the scientific ML. And it's the same thing which happens with all problems. So someone has asked about weather and turbulence, right? It's the same thing. You identify an ODE or PDE, replace missing physics with neural network. So this is the step number 4, defining the UDE. Now I want to show you one thing. Before we move to optimization, the neural network is not optimized, right? So it will not actually mimic the underlying data pretty well. So let's see how the neural network is doing. So this is the plot. So the blue is the underlying data and the orange is our universal differential equation prediction. And as expected, it's a very bad prediction, right? It's not matching very well with the underlying data because we have not yet optimized the neural network. Remember, optimization needs to be performed. And that's the next step which we are going to come to. But this is initially the weights of the neural network are initialized randomly. So it's not matching the underlying data. And that's expected, as I mentioned. We have not performed the optimization. And now we are going to step number 5, which is the optimization procedure. Here we are going to be using the Adam optimizer with a step size of 0.01, correct? And I'm going to just run this to show you the optimization now. So let me actually run this right now. Okay, so I'm going to run this and please keep an eye out on the plot. So I've run this right now and I'm beginning the optimization procedure. It will take some amount of time because you see now the neural network is trying to learn. See, can you see the updating orange graph? It's the iterations of the neural network. It is trying to learn the underlying data as we proceed. It does make some mistakes, but here you can see now it has started matching the high frequency areas and the high amplitude areas pretty well. It's still making few errors over here, see. But as the training proceeds, you will see that the neural network starts doing a better and better and better job over here. So right now the training is still ongoing and I think, so I'm running how many iterations over here? I'm running 100 iterations over here. So you'll see this plot actually superimposing for itself for 100 times. And let's see how the thing is towards the end. There are several questions in the chat which I can meanwhile answer. Could you explain what you mean exactly by multiplying the NN to Newtonian? So what we are doing is that, let's say there is a term in the ordinary differential equation. We are multiplying the output of that term with a neural network. Essentially, let's say an ordinary differential equation dx by dt equal to x square. But what if it's x square plus something? So that plus something or that multiplied by something is replaced by a neural network. That's the simplest way to think about it. What's the application of SciML in real life? I'll come to my project, which I did during COVID-19. That's one of the best examples which I can think of. So here you can see the plot has been done for 100 iterations and now the neural network matches very well with the data. Perfect. Now I'm going to actually just visualize the results a bit. Don't worry, this is the last step of this, but this is a very cool graph. So here is the visualized results. Okay. So first focus on the truth. The truth is the blue data. The Newtonian physics is the green data. And as you can see, it does not match very well because it's not the correct equation. The orange is our UDE prediction. And you can see that the universal differential equation prediction actually matches the underlying data pretty well. That's amazing, right? We did not know what the missing physics was. This is just the neural network which is optimized. And now it is matching the underlying data pretty well, which means that without knowing the missing physics, now we have a model which captures the missing physics through a neural network. So you can see the orange and the blue lines completely overlap with each other. That's the power of scientific machine learning. Here you are essentially combining science, which is the missing ODE, with a neural network to replace that ODE. Some great questions have been asked. How do you know whether to multiply or add NN, right? That's a very good question actually. And that's a question which takes some time to answer. The way you can actually try addition also. And I think the best way to do is trial and error. I tried addition first, but it did not result in a good prediction. So then I tried multiplication. This whole process is trial and error. There is trial and error involved in hyperparameters. Like you may be thinking, why did I choose a step size of 0.01? Why did I use the cosine activation function over here? Why did I use 32 units? It's all a process of trial and error which leads to the optimal loss function. Even here, you can add it like as you are saying, we can add a plus sign here. It's very flexible. In Julia you can do simple, you can even do a squared sum here. You can do whatever you want. It's very flexible interface. That's why I like Julia. In Python it's very difficult to do this flexibility, but essentially this is where we have reached. And some nice question has been asked in the chat. Many of you are thinking that can it spit out the actual equation, right? We have discussed, it has recovered the missing physics, so it has matched the underlying data, but what about the physical representation? And it turns out that it can be that. We are not going to cover that in today's webinar, but it's actually called symbolic regression. So Cindy Julia means it, so it's a symbolic regression. What it basically means is that we can recover the underlying equations based on the data alone. The last step of this is the optimized neural network. You can run it through a symbolic regression, and then you can actually understand the underlying symbolic equation. And it turns out that when you run the neural network through symbolic regression, it exactly recovers the relativistic physics like this. It exactly recovers the relativistic physics. It recovers this cosine term on its own. So that's what makes scientific ML interpretable also. You have replaced the missing term with a neural network. And that way it's pretty intuitive to think of the story. So we have now recovered the missing physics without knowing the Einstein's relativistic equations. That's amazing. And if you have done a project like this, you can then convert it into a research publication very easily, because not many would have done this. I'll be sharing the code with you, and you can interact with it. You can play with it. Many people have asked how much time do you need to devote to learn SciML. I'm coming to that in the subsequent steps. First thing which is very important and which I've also mentioned over here is that if you just want to quickly go through some ML videos, the 3 blue 1 brown videos are one of my favorite for machine learning. I will link 3 videos over here. They are some of the most interactive and visual videos for a quick overview. If you want a detailed overview, go through these playlists, the ML Teach by Doing and the neural networks from scratch. This is the only ML you will need for understanding scientific ML. And of course, you will need some basic understanding of the Julia programming language. Okay, so please share the list of resources document. I already shared it earlier in the chat, but let me share it once more. Okay, so here's the document. Please go through this once more. Okay, now I just want to quickly show you some research papers which have implemented scientific machine learning. So code link, I'll not be sharing code link. I'll be sharing with you the code file through email at the end of this webinar, or tomorrow. Maximum you'll get it by tomorrow end of day. So at the end of just this takeaway is that if you belong to any of the field, right? So let me go to this Google forum. If you belong to any of these fields, after this webinar, what you can do is think of an ordinary differential equation or a partial differential equation which shows up in your field. If you do not know, just ask Chat GPT or Google about it. I'm pretty sure all of these fields have an ODE or PDE. Then think about what parts of that ODE or PDE you can replace with a neural network. That is the start of an amazing research problem, or an amazing scientific machine learning problem. Okay, so this is the whole essence. Okay, replace parts or the full ODE with a neural network, and with this you can discover properties which were not known. One of the best applications is discovering materials. So scientific machine learning has been used to discover new materials by just replacing some properties or terms with neural networks, and by optimizing the neural network. Amazing, right? So let's go ahead a bit. Okay, so before coming to the problems which scientific ML can solve, which I'll go to in a bit, I just want to clarify. So many students have asked about how do I learn scientific ML, right? So if you find all of this interesting, check out this bootcamp which we launched in January. It has become extremely popular now because it's the world's first scientific machine learning bootcamp. So if you look at the bootcamp content, here is all what we'll cover. If everything is new to you, we'll start from the basics. We'll teach you Julia, ODEs, PDEs, physics-informed neural networks, neural ODEs, universal differential equations. Today was just, I would say, 1% of what is covered in this entire bootcamp. So we also have a list of projects which we do with students enrolled in the researcher plan. Let me load this link again. So someone was asking about astronomy, right? Look at some projects which we have done with some people, and Rajat will be sharing this in a bit more detail. But we already have collected a bunch of research project topics for epidemiology, physics, mechanical, chemistry, economics, material science, astronomy. All of these projects, we have already curated the topics. So people who enroll in the researcher plan, right? We are already, so there are 40 people who are enrolled in this plan up till now, and we have reached the final stage of publication with many of them. Rajat will show you what these people are working on, but essentially we're trying to publish in many fields. Here are some cool projects which you will also be doing as part of this bootcamp. Here is a physics oscillator project, and so many technical doubts are being asked right in the chat. Many of this will be clarified in the bootcamp. Right now, there is just not enough time to go through everything. If you are a student and affordability is a bit limited, you can just start with the student plan, which does not have the research publication. But if you are a working professional, or if you are applying to grad school and if you want publications, right, try out for the researcher plan. Next batch is starting on August 4th. This month's batch are full, so we don't have any more seats left for this month. So I hope everyone has got link to this bootcamp in the chat. Just go through this, look at the content. I hope now you will understand this website a lot better after today's lecture. Just go through, access the bootcamp PDF, go through the curriculum, go through the different plans, and just email us at hello@flyvidage.com. So I'm just sharing this email address in the chat. If you are interested or just have any doubts about anything, just email us over here and we can see about enrolling you for the next month. Okay, now before we come to Rajat's part, I just want to show you some scientific machine learning projects which have been already implemented in literature. And if you go to the document and see the last section, you will see some papers in the fields of civil engineering, battery, combustion, epidemiological modeling. So let's go through the first paper. This is a civil engineering paper, right? Other people may think that it's a 30-page paper. So I will not understand this. But now people who have gone through this webinar know that first you look for an ODE. So here are the set of ODEs which these people have. All they have done is replace some terms of this ODE with a neural network. That's it. Now let's go through another paper, which is battery degradation, 30-page again. So people who have not joined this webinar will think that quite complex, right? I'll not understand. But again, as I mentioned, scroll down below and look for the ODE. This is the ODE which these people are using. This part, this is the ordinary differential equation, right? And all they have done is that they have added or they have replaced terms with a neural network. See, this is exactly what we learned in today's workshop. And that has led to this high impact publication in battery degradation for these people. Then there are projects in the field of chemical reaction. This is my paper in the field of epidemiology. You can take a look at it. This paper got me my PhD. It got me all those job offers. It was released right in the middle of COVID-19. Overall, this work has around 250 citations now. And you can see I started with the SIR model, which I showed you, right? And then the only thing which I've done is replaced one term of this SIR model with a neural network. But I think you will really enjoy going through this paper to see how what is the story which I formulated. And I really connected it with real life, with the infections in Russia, UK, Spain, Italy, etc. And I actually showed the results for, so here's, I showed the results for Europe, showed the results for USA and essentially India, all the countries. It became a really famous project. So we were featured on the Fox News, Indian News, and many other news outlets. So this is the impact which scientific machine learning can lead to. Okay, so that brings me to the end of my part. Now I'll switch to Rajat. Well, Rajat will show you the kind of papers and the kind of work students have been doing in the bootcamp.
Okay, so I will be sharing two examples of students who have started to publish papers as a part of the bootcamp. And these two examples are actually real life examples. They are related to different fields. So let me just get this screen down. Just a second. Okay. So this is the first paper which I wanted to share. It's a paper which uses scientific machine learning. For some reason, I'm not able to zoom this out. Yeah, okay, now it's better. This is a paper which uses scientific machine learning for modeling the chaotic Lorentz ODE system. So this particular student was a beginner in the field of ML, but he was very interested to apply scientific machine learning for a problem related to climate modeling. And the basic governing equations which are used to represent this problem are the Lorentz system of equations, which are these three sets of ordinary differential equations. And you can see there are three variables x, y, and z. These system of equations are very interesting because they represent a system which is chaotic in nature. So what do I mean by chaotic? Let's say if we consider the motion of a simple pendulum, that motion is not chaotic because whatever input I give, the output is pretty much fixed. In a chaotic system, what happens is that a small change in the input can lead to drastically different results. And Lorentz system has been used to model the temperature fluctuations as well. Here we are modeling the atmospheric convection using these Lorentz system of equations. The first thing I want to help you understand is that if you think that if you are a CA student or someone who has lost track of differential or partial differential equations, these equations you can see are not very complex, right? First of all, they have simple terms and they are easy to understand, and you don't need to know their solution in depth in order to analyze this problem. So that is not really the crux of scientific machine learning. So that is the first thing you need to know, is that even if you have lost touch of differential equations, you can still solve this problem using scientific machine learning, which was the case with this student. So after writing the abstract and the introduction, we directly jumped on to the methodology. Here what we have done is that, so if you want to see how the graph looks like, yeah, so this is how the butterfly effect looks like. Essentially, it goes around in a loop and every single loop is different. And a small fluctuation will completely change the trajectory. Here we fix these three parameters, which are sigma, beta, and we assign them a fixed value. So these are Prandtl numbers, Rayleigh numbers, and geometric factor. It is completely fine if you're not able to understand this for now. Now, what we have done is that we have analyzed this problem from two different, let's say, concepts. One is neural ODEs. So we have not really covered this as a part of today's webinar. So let me just skip it for now. I will go to the second part, which is universal differential equations. So generally what happens is that, let's say you have collected some data and you're using some set of equations to model that data. But what is the proof, right, that these equations are actually correct? What if you have got some data and when you actually map these equations, it turns out that the equations are not really matching with the data. So you have some knowledge, but that knowledge is incomplete. And the main use of these universal differential equations is that we don't assume a lot of things. Of course, some things are assumed. Let's say some scientific structure is maintained over here. As you can see, I have maintained the sigma y, but there is a neural network term which is being added in the first equation, which says neural network subscript of 1. And we are using three different neural networks in these equations, which we want to train to match the data that we already have at our disposal. And this is really the crux of scientific machine learning. Whichever problem you take, the equations which are known in the literature are only approximate equations. So as you might have known the saying that every model is wrong, but there are some models which are useful. So this is finally a model, right? These Lorentz set of equations, but it's wrong because the true equations are going to be something completely different. And by using universal differential equations, we are trying to nudge a step closer to the true form by approximating these by these neural networks. And then what we do is that we optimize the hyperparameters, the optimization functions, uh, and the activation functions, and we try to match these neural networks with the true or the ground truth, the data that we have. And you can see the matching is being, so this is for the neural ODEs. For the universal differential equations, this is how our model performs. So you can see the red dots are the true values, red, green, and blue, and the predicted values are shown in blue. So this is the main idea. So this paper is almost complete, and we'll be submitting it to a very good journal, and we are confident that it will be accepted in a journal which is impactful, because people have studied Lorentz equations before, and they have studied climate models before, but no one has studied this practical problem from the lens of scientific machine learning, and that is the novelty which this paper is bringing out. The second paper which I want to share with you is yes. So the second paper is actually related to the field of astronomy. So I can see that many of the participants in today's call have background in astronomy, and this is one of the fundamental equations, which is Chandrasekhar's white dwarf equation. This equation is a bit complex because it is, first of all, it has a number of terms, and it, like, when you look at this as compared to the Lorentz system of equations, you don't feel a lot of comfort when you see this equation, which is because it has these complex exponents, etc. But that is the only complexity you are going to encounter when you are looking at these at this equation. And this was the problem which was tackled by another student who approached us and who said that I am very interested in astronomy and I have some basic knowledge of ML, but now what I want to do is that I want to apply this knowledge of ML to astronomy so that I can boost my profile, and when I'm applying to grad school, I can have a paper in my name. So here also we are doing a comparative study of neural ODEs and universal ODEs to solve the Chandrasekhar's white dwarf equation. And as I said here, we are looking at this equation, which is a bit complex, but it's also very interesting. And once you understand the different variables and the boundary conditions, that is all the initial knowledge that you are going to require. After that, it's just a matter of training the neural network to match with the data. And here also the kind of output that we get is very promising. We have trained this neural ordinary equation, a differential equation, as well as the universal differential equation on the data, and it performs really well. So you can see these graphs, the trained UDE. So the ground truth, so we have also added some noise to it. So what we generally do is that if the data is not available from any literature review paper or any paper, we assume some data from the equations which are known in literature, and we add some noise to it. So then it becomes noisy data, and then we assume that to be the ground truth, and then we try to train the neural networks to match with this ground truth data. So the process is very similar as you saw in the climate modeling case, as well as this case, which is in the field of astronomy. And here we actually do something more. We also go ahead and do forecasting, and this is where the practical use of the methods of scientific machine learning lies. Because okay, you are fitting a neural network, but what is the use of that, right? Okay, like people can ask, let's say a reviewer asks that you have used a neural network to fit the ground truth data, but what next? The next thing that we can do is that we can forecast. And Dr. Raj also did the same thing when he used scientific machine learning to solve the epidemiology problem, where we have the data of the infected patients and we are using a neural network to train our model to match the data. The advantage here is that we can forecast for the next 1 week how are the infected patients going to increase, and that data then can be used by hospitals to better plan the number of resources in the hospitals, which include the hospital beds, cylinders, etc. So initial part, of course, is training the neural network to match the ground truth data, but it doesn't stop there. There are two more things you can do. First thing you can do is that you can forecast. Second thing you can do is that you can try to apply symbolic regression to the neural network to uncover the missing terms. We have not really covered that in this webinar so far, but that is a very, very interesting step. And that's when you can really, because people usually think that neural networks is a black box and you don't really know what is happening inside. But once you apply symbolic regression, you can actually find out some terms which are matching with the ground truth data. So let's say you try a series of terms, let's say x square, x cube, x raised to 4. And then you try to see which term of this has the best accuracy. And that becomes the degree of the polynomial in your neural network. So this is just some basic understanding of how symbolic regression works. But Julia language we are recommending because Julia has inherent libraries for doing symbolic regression. And the advisor of Dr. Raj, Chris Rakaukas, he is the main developer of all these libraries. And that is why we are very closely aware of how Julia can be used. And for both of these papers, which are in two different fields, we have used Julia language to do all the steps, including the training, the optimization, and the forecasting as well. And the last paper is, of course, the paper by Dr. Raj, which he had described. These are the differential equations which are inherent in that problem. And these are also quite simple to work with. The addition which Dr. Raj did was that he changed these equations to this equation. So you can see how a neural network is added over here, plus. And then we try to recover these neural networks by matching it with the ground truth data. And the forecasting that the level of forecasting that it does is simply amazing. So what this paper really proposes is that it proposes a new term, which is the quarantine term, which looks like this. And what is the use of the quarantine term? Well, basically you can, if you look at the inflection point in the quarantine term, you can understand when is the lockdown imposed by the government, because after the lockdown is imposed, the quarantine strength is going to increase. And if there is one, let's say, metric by which you can track when the quarantine is increasing, you can find out the inflection point. And the green and the red, the green is when the government actually imposed the lockdown in Spain, and red is the prediction of the model. So you can see how close it is, which means that our model is actually able to predict that based on the data that we have received, probably the government has imposed the lockdown, and we are not off by more than 2-3 days. So it is pretty close. So this is the usefulness of scientific machine learning. Once you approximate it with a neural network, that neural network can be used for forecasting, and it has incredible uses if you learn the forecasting. And symbolic regression is, of course, another sector. Some of the students in the researcher plans are working on this, some of them are not. So it depends on whether we find any logic in doing symbolic regression. And if it's very difficult, then we leave that problem. But in some cases, it is easy to do symbolic regression as well. So then we approach that problem from that lens. So these are just 3 examples, but there are a lot of students working on different problems. And I'm sure if you are interested in one particular problem and you have known the governing equation behind that problem, we can look at that equation from a scientific machine learning point of view, and we can gain some interesting insights by applying SciML. So this brings us to the end. I think we are almost close to 8:30. I'll just stop sharing my screen.
Yeah, I'll just share my screen to answer some of the questions in the chat. So first of all, there is a question to integrate SciML with finance, right? So as I said, no need to be restricted to any field. In finance, there is an equation called Black-Scholes equation, which models the stock price. If you, let's say, replace this term with a neural network and try to recover it based on the data, I'm pretty sure you will be the first person working on this project. It would lead to an extremely impactful project. Secondly, someone asked about the combustion paper, right? So here is that paper I've shared. The links are all there here in the document which I shared, but let me just show you what they have done. They have also started with ordinary differential equations like these, see? And they have replaced the right-hand side with neural networks. Basically, there are many questions coming in the chat for integrating CFD plus ML, then let's say neuroscience with SciML, etc. All of these have SciML applications, but we cannot cover everything right now. I hope we have showed you enough today to make you motivated. So the main purpose of this workshop is not just to show you the black hole project, but to also show you the tools necessary for you to come up with your own project, own scientific ML project later. So that way, it's supposed to be a webinar which also teaches you what to do after the webinar. So as I said, the first thing to do is identify ODEs, PDEs, then come up with a SciML story. We'll also be sharing this recording with all of you. So no need to worry. And we'll be sharing it by end of day tomorrow. So I think we are almost at the end of time. Rajat, do you want to say any last?
Yes. So we tried to cover a lot of things in this session, and hopefully it was a good introduction for all of you in the field of scientific ML, and we hope it really motivates you to get started in the field. We see that a lot of students do some basic course on ML either online or through their college, and they do a toy project, but they don't really try to do a very exciting and real life project because there is a mental block in their mind that going from basic ML course to that practical project is a very big gap, but actually it's not. And our one of the main aims of this webinar was to tell you that that bridge is not that difficult, and SciML can be that bridge. So we encourage you to get started, first learn the basics of ML, then directly get started with a real life impactful project without wasting time. That will help you not just in your placements, but also if you want to apply abroad, it can help you in building your research profile a lot. So thank you very much, everyone. I'm just sharing our email address at the bottom. If you have any queries or if you're interested in any one of the bootcamp packages, just email us on this email address.
Thank you, everyone. And we'll be conducting many more such sessions. So stay tuned for the next session, which will be coming up next month. And the bootcamp registration date is 4th August for the next batch. So please email us before that if anyone is interested.
And one last thing, maybe we can take a screenshot with all of us. If we can, if all of you can just enable your video, we'll take a screenshot with all of us doing a pose like this, so that yeah. So I encourage all of you to open your cameras. Okay, I'll just wait for some seconds so that all of us will...
Guys, don't be shy.
Just a second. Raj, can you get the screenshot? My
Yeah.
they are not.
Okay, almost done. Okay, done. Thanks, guys.
Okay, thank you, guys. Bye. Thank you so
Thanks,
much.
everyone. Thanks a lot. See you. Bye. Bye.